All right, so this is the last titration video. If you are looking at your notes, just remember that table on the first page of the titration section. This will be filling in the last column of that table. You're going to notice that it mirrors the weak acid strong base titrations very closely. Pretty much the exact same thing's going to be happening, just in the opposite direction. Initially, in a strong acid weak base titration, all you have present is a weak base. So you're going to find the pH by using the equilibrium dissociation of that weak base, the fraction that actually does dissociate and produces hydroxide ions. Your pH will be basic at this point. Um, Once you start adding the strong acid and neutralizing the weak base, you'll make conjugate acid and you'll have a buffer. You'll have a buffer up to the equivalence point. And so you can find the pH of your buffer mixture using Henderson-Hasselbalch. The only time you can ever use Henderson-Hasselbalch is with a buffer when you have both of the components present. But to use Henderson-Hasselbalch, we have to neutralize the strong acid that's been added. So we have to do a stoichiometry problem first to figure out how much of the weak acid is made and how much of the weak base was consumed. You can also determine the pH using your equilibrium expression if you include both quantities, weak base and conjugate acid. At the equivalence point, you will have consumed all of your strong acid and your weak base. So the only thing that will be present that will influence the pH will be your conjugate acid. You'll have to determine the concentration of that conjugate acid and then use the Ka expression for that conjugate acid to determine the pH. The pH should have been decreasing gradually up to the equivalence point, but once it reaches that equivalence point, it should be acidic. After you have passed the equivalence point, you will have two components upon the stoichiometric component being done that will influence the pH. You will have both strong acid and weak acid present. Strong wins over weak. Figure out the concentration of the strong acid that remains in the mixture after the stoichiometry problem has been solved, and use your pH equation to find the pH, accounting for the diluted volume between the two species that were mixed together. And again, I'm sorry I left out room for y'all to write equation in that last box in the table. So we've got 5 different problems to do with this type of titration, similar to what we did previously. Um, you'll notice here this graph, it's pretty much the, again, the mirror image of what we saw with the weak acid strong base, but we start out basic. We have our buffer region. We reach our equivalence point in the acidic range, and then we very quickly drop to being more strongly acidic since the strong acid is dominating the pH determination at that point. And again, once you know your halfway point, once you know the volume that has gotten you to the point where you have equal amounts of the weak base and the conjugate acid, you would double that to get to your equivalence point. All right, so we're going to be dealing with ammonia, and we're going to be adding nitric acid to it. We'll notice with this first problem, we don't have any nitric acid being added. All we have is the ammonia, NH3, present. And so I went back through and fixed my arrows. Ammonia will dissociate in water partially to produce ammonium and hydroxide ions. The Kb value for ammonia you can get on your chart, 1.8 times 10 to the negative fifth. Since the weak base is all we have present, we can use our Kb expression to determine the hydroxide concentration. Again, the Kb value, 10 to the negative fifth, and the concentration, 10 to the negative first, are far enough apart from one another that we can exclude the minus x that would come after 0.1. When I did it in the calculator, it did not change the value of x, which was 1.3 times 10 to the negative third, or 0.0013. That is your hydroxide concentration, so you would use that to find your pOH. And once you have your pOH, you can calculate your pH by taking 14 minus the pOH value. Since all we had was a weak base, we would expect our pH to be basic, and it is indeed basic. It's not super basic, but it definitely is basic. In part B, now we're going to start to form our buffer since we will have some strong acid that is being added to the weak base. We'll need to find the moles since we're dealing with stoichiometry of both components. Do that by multiplying volume times molarity. I got 0.0100 moles of ammonia, and I got 0.00500 moles of hydrogen ions. I have no ammonium ions that are formed at the initially. All I have in the mixture is the ammonia and the hydrogen ions from the nitric acid. So between the two reactants, the hydrogen ions are my limiting reactant. So that's the amount that is going to be taken away from both reactants, and that is the amount that is going to be formed of ammonium ions. You'll notice we have equal amounts of weak base and conjugate acid. So this is when we are at the halfway point when the two are the same. If we substitute these into our Henderson-Hasselbalch equation, one of the things that's nice is whether you're dealing with a weak acid strong base titration or a weak base strong acid titration, that Henderson-Hasselbalch equation doesn't matter. You can use it to find the pH of either. I take the negative log of my Ka. Remember, we had ammonia, which had a Kb value. The Ka value would be for ammonium, and we would get that from our chart or by using Ka times Kb equals 1 times 10 to the negative 14th. We take the negative log of that Ka value, and because we want the base in the numerator, the 0.005 would go for ammonia in the top, and the 0.00500 moles of ammonium ions would go in the denominator. The log of 1 is 0, so the pH would just be your pKa. That, again, is your halfway point when you have equal amounts of weak base and conjugate acid. In part C, we're going to still be in the buffer range, but we're going to be past that halfway point. We'll find the moles again like we've done previously using the volume and the molarity of the two components being mixed together. This time the hydrogen ions are still our limiting reactant because we still have a smaller amount of them present. So that's the amount that's going to be taken away from both reactants, and that's the amount that's going to be added to our product. When I do the math for that, the stoichiometry, I get that I have used all my hydrogen ions, but now I have more acid in the form of NH4 plus than I had of ammonia, NH3. When I find my pH using Henderson-Hasselbalch, because I have more acid present, I'm going to see that my pH is going to have continued to decrease, and it's now down to 8.77. I told you in the previous video that if you were going to try to solve for pH using your Ka or Kb expression with a buffer, that you had to change those concentrations or change them back to concentration. I checked it out between videos, and because it's a ratio, you do not have to. You can leave them in moles, but to make your lives less stressful, I would say that whenever you're doing anything with Ka or Kb, if you're not sure, make sure you have substituted in concentrations and not moles. Henderson-Hasselbalch moles are fine, but with Kas or Kbs, you really have to make sure you know what you're doing before you leave them in moles. So just change them for concentrations for your sake and mine. Okay. In part D, we're going to have reached the equivalence point. We've doubled the volume we had at our halfway point. We're up to 100 mils. So we have equal amounts of the ammonia and the hydrogen ions. So both of them are going to be consumed. They're both limiting. And the only ion we have present in our mixture is the ammonium ions. And we also have water, but the weak acid will win out over water. Since the only ion present is a weak acid, we cannot find the pH using Henderson-Hasselbalch. We have to have weak acid and conjugate base to use that. So we would need to use the Ka expression for ammonium to determine what the pH will be of our mixture at this equivalence point. Remember, the pH should be acidic at the equivalence point, and we only have an acid present, so that makes sense. With ammonium, we would take the moles that we have of it and divide it by the new volume to get its adjusted concentration, 0.05. When we set up our K expression, we need to make sure we use the Ka because we're dealing with an acid, which is donating protons. So we would use 5.6 times 10 to the negative 10th as our Ka value. Our x squared would be in the numerator, and the new concentration of ammonium, the 0.0500, would be in the denominator. That is 8 powers of 10 different from our K expression, so I think we're okay with ignoring the x. And when we solve for, or zero point zero 0.05 minus x, when we solve for x with that expression, we get that it has 5.3 times 10 to the negative 6 molar. And again, that is the concentration of your hydrogen ions. So we can go directly to pH with that. And by taking the negative log of 5.3 times 10 to the negative 6, we get the pH is 5.28. Acidic, which is what we would expect at the equivalence point since all we had was the acid. Finally, we have part E, which is when we have added excess acid to our mixture. We still have the 0.0100 moles of ammonia, but now we have 0.0150 moles of hydrogen ions. So with that in mind, the ammonia is going to be our limiting reactant. We're going to take those moles away from both reactants and add them to our product. And when we do the math through stoichiometrically, we get that we have about twice the amount of ammonium ions in moles as we do of hydrogen. Hydrogen, being a strong acid, is going to win out over ammonium, being a weak acid, in determining the pH. To find the pH of this mixture, we have to account for the new volume, the 100 plus the 150 mils, so we get 0.2500 liters, and the concentration of hydrogen ions present is 0.02. When I find the pH of that value, I see that it is very acidic, which is what we would expect with a strong acid, 1.70. Now, that's the end of what you have in your notes. I'm going to briefly touch on indicators. This was the last lab that we did. And if you were given choices for indicators, or if you were given a chart and told what range the pH changes in, you should be able to identify an appropriate indicator that would be used in a titration based on the pH of the equivalence point. We want to find indicators that are going to change color close to the equivalence point because that's when we want to know that our reaction is complete. We have consumed both reactants fully. So pH indicators are typically organic substances. We've been using phenolphthalein a lot this year, but in your last lab, you got to see a universal indicator and bromethymol blue. I think it was a methyl orange, but bear with me on it. I don't have it right in front of me. And we've saw that pH indicators will change colors at different pHs depending on the Ka of those organic compounds. So this is an example of a chart. You can see here why we use phenolphthalein for basics solutions that should change at a basic pH or close to neutral because it changes colors around a pH of 8. We use bromethymol blue in our last lab, and that one changes colors from yellow to green to blue between 6 to 8, so right around neutral. Methyl orange changes colors around a pH of 4, so more of an acidic range. So we pick indicators based on the pH at our equivalence point. We would not want to use bromethymol blue. Sorry, let me find bromethymol blue on here. We would not want to use bromethymol blue for something that's going to change for a weak acid strong base titration because we would expect the pH of that to be more basic. We would not want to use bromethymol blue for a strong acid weak base titration because we would expect the pH for that mixture at its equivalent point to be more acidic. We would use bromethymol blue for a strong acid, strong base titration because that's when we have used up both components of the reactants and water would determine our pH, and it would be at a neutral pH, so that would be more appropriate use for it. So basically, you're looking for an indicator that would change colors close to your equivalence point. It doesn't have to be right on, but you also don't want to pick one that changes colors in an acidic range when you know that your equivalence point is going to be more in a basic range. Okay?